Hi everyone, this is Vedant Tushar Mehta. My teammates are Aarav, Pranav, Shah and Neel Asheshbhai Shah. And this is our presentation for the project of data mining. Our topic is call volumes prediction for optimal resource allocation. And we have used the police calls 2023 dataset for that. So let us understand the problem which we are trying to solve right now. Um, there are there is a lot of crime happening in any city, and emergency units generally place themselves based on intuition, and they do not leverage the use of predictive data or real-time data. Like if they can use the predictive data, then they can allocate the resources much more clearly or in a much more better way. Due to these reasons, there is delayed response time. Like sometimes the response units are not able to locate to the place in sufficient time, and there are certain geographical disparities too. Like some areas might experience more crime, and these areas need much more response units situated there. So with the help of the police 2023 dataset, police calls 2023 dataset, we are trying to solve this situation. Our goal is to predict call volumes in the future. So based on the date and time given, we can predict the number of calls the department can receive from any location in San Jose. So what we'll be actually doing is that we will be dividing the map of San Jose into different hexagons, and those hexagons will have a certain value to it. Based on that, it will give a visual idea regarding the number of calls which can be expected from that area on that day, on that particular time. So I'll just recap about what things which we had achieved till our midterm presentation. So through visualization techniques and through exploratory data analysis, we had inferred some information about our data set, like which attributes are important and how many missing values are there and how much should we consider while creating some models on this data. And we also came into some problems, like we wanted to map the addresses to a certain latitude and longitude, and for that during our midterm we used the nominatim API. We also pre-process the data by clearing or by removing the null values, and after some thinking we came up with a solution that we will be creating hexagons, and that is what Uber uses on their mapping service to like distribute the pieces of maps into hexagons. So that's what we thought of while implementing. And we also assessed the primary preliminary results of k-means algorithm and dbscan, and the problems which we faced was that k-means and dbscan, they were given like spherical groups, and that was creating many overlapping boundaries in our dataset, and due to that many points were being considered again and again. So we wanted something much more clear and discrete boundary to separate the areas on the map. So following after our failures during the midterm presentation, like the shortcomings which we had in our algorithms, we decided to move on to some other different algorithms. So cover over we will cover those algorithms over here. So the first problem was nominatim API, which we were using during our midterm, was quite slow. It was timing out very frequently, and there was not like much limit on that API. So we came up with another solution. Google Maps geocoding API was allowing a lot of hits to it. Approximately around 50,000 addresses were converted from the address string to latitudes and longitudes, and we did that. And other after that, it was a paid version, so we were not able to leverage more of the Google Maps geocoding API. But yes, we created a data set like this of latitude and longitude, which were mapping to the particular address values. After that, we added the latitude and longitude columns to our data set. So I'll go back to the previous slide. So this was needed because in our model we needed numerical values or something encoded which contains a certain meaning for model creation. And if we directly used address, or if we encoded the address, then it would not have a certain meaning. So converting it to latitude and longitude was very important. Then the three parameters which were required for our model were the latitude, longitude, the daytime. So this was a time object. So we required a day of the week and the hour. So at what time the user wants to predict the crime which is going to happen, and at what day of the week. So based on our previous data, we based on our previous data, we we were given an offense date. So we distributed the offense date to the day of the week and the hour which was already given. So we extracted the day from the offense date. After that, we had already pre-processed the data for like 40,000 rows. So we had converted 40,000 address values to latitudes and longitudes, and we converted another 16,000 to latitudes and longitudes. And after that, we merged them, and we did some cleaning on the data because there were some unnecessary rows which were there after we got the necessary attributes. So offense date, that was unnecessary because we had already gotten day of the week and hour. Then offense time, which was also not required because we already had hour. So we removed those attributes, and finally we had this table. We had these attributes which were necessary for our prediction model. Now, here comes our main part. This allows us to, the hex ID is a function, like the hex ID. H3 is an library in Python which allows us to create hex ID, and hex ID is an ID, you can say that on a map you can put a hexagon, and that would cover all the area which is coming inside it. So the resolution value is how much detailed the hexagon should be on the map of the earth. So based on a latitude and longitude, we can convert, like we can divide the map into different hexagons, and all of this latitude and longitude which come under this hexagon will be mapped to the same hex ID. So that is what we did here, and we converted all our latitude and longitude to different hex IDs, and we had lots of latitude and longitude, around like 50,000, but the unique number of hex IDs which we got after converting them was around 2000 probably. Yes, around 2000. And we also converted the priority in reverse order, like we wanted the priority to be higher if the danger was higher, so we subtracted it from 7, so that it can be reversed. Now after that, we also wanted to get a idea about the weighted call count. So if the priority is higher, then we are mapping it directly to, like, let's say if someone has a call priority of 1, which is a very low priority, then that call is considered only once. But if call has priority of 6, then we can say that 6 different calls of priority 1 were there. So this is our weighted call count, which means that 4 call counts were there of single priority. Now here we group the attributes, like with the unique attributes which we have are hex ID, day of the week, and hour, and we group them based on that. So given a hex ID, so in an in an hexagon, on a particular day and a particular hour, how many calls are being made from that particular hexagon are grouped using this function. So one problem which we ran into after doing this was that the distribution was very skewed towards 0. Most of the calls, like the actual call count was very low, and the like frequency of lower call counts was very high. So the call count from a particular hexagon was 1 most of the time, and some hexagons only had a higher number of call counts. So this was creating an imbalance in our prediction variable, which was call count. We basically wanted to predict the number of calls from a particular hexagon. So due to this imbalance, we initially were seeing some bad results in our data. But to address this, we upsampled our data by like duplicating the samples which were having less frequency. So we made all of the frequencies equal, and after that we added the upsampled rows, and you can see that previously our data had around 29,000 rows, but after upsampling our data has around 300,000 rows. So this made our data set somewhat balanced, and due to that, our model was predicting very precisely. Now let's get into the details of our ML algorithms. So we encoded the hex ID and day of the week using label encoder, and we trained, test, and split the dataset. After that, we implemented this four algorithms: random forest regressor, linear regression, gradient boosting regressor, eta boost regressor, which had number of estimators 100, and the R squared error was closest to 1 for random forest. It was pretty close, 0.99. So this was the best model out of all of these four models. We also wanted to implement a neural network. So we created a sequential model and added 64 layers, 64 neurons in the first layer, 32 neurons in the second layer, and 16 neurons in the last layer. And after that, the last one was our output variable. And the training and validation of graph can be seen here, and the R squared error was R squared value was quite low. It was not much close, like it was not close to one. So random forest was the best one. So this is our user interface. We have created it using Streamlit, which is a web framework using Python, and it allows us to create like responsive websites. And we have a slider for picking the hour of the day and selecting the date, and based on that, like for different, so here you can see for 13th December 2024 on 22, so that is 10 p.m. Downtown is pretty unsafe, you can see that. But on 12th December at around like 4 in the evening, the downtown is pretty much safe because more crime might be happening at night. So this like gives us a general idea about our model working. So how do we create our user interface? We iterate over all the hex IDs of San Jose which we had created, and we predict based on the date and time. And if the predicted call count is high, then based on that detail, the hexagon is colored red. And if the call count is low, then the hexagon color is green. And this is the tech stack which we had used. We used CMPE, Folium. Folium was used for creating the map. Network X was used for exploratory data analysis, and TensorFlow, and these are all the basic libraries. Pickle was used to export the random forest model and use it in our front end. And our future works include, like, we want to add real-time streaming of call volume data so that the predictions can be very up to date. And we also want to perform some hyperparameter tunings for the random forest and ANNs so that their performance can also be improved. And another thing which we can add is that we can expand our project to include different cities as well, and give some recommendation about how many resources should be allocated. Right now we are just predicting the call count. And the last work that we can do is that instead of like duplicating the values to handle the class imbalance, we can use some good technique like smooth analysis. The most naive solution was to duplicate the values, which we did, but this is something clever which we can do in future. So I'll head over to our UI, and this is our UI. So let's say right now, if I change the date to be, let's say, 25th of December, and okay, it is predicting for 16, like so, 4 o'clock. But if I change it to around, um, let's say 11 o'clock at night, so you can see that it is pretty safe over some areas. We can see the predicted calls is also being displayed at the particular XID. So this area is pretty unsafe. This area is pretty unsafe. So the resource provisioning can be done very easily if we have something to look up to. So yes, that is our whole project. Thank you.